Number 15, which of the following molecules will have a Lewis dot structure with exactly one unshared electron pair on the central atom? And really there's no way to do this other than to draw out the Lewis dot structures. Hopefully water you should remember by now, and if you can do that with some of them, it sure does speed things up. So I'm just going to draw water first. So here's water. You remember that it has two lone pairs on it, so that's not going to be the answer. We're looking for one with exactly one unshared electron pair. Just to kind of remind you the proper way to draw Lewis structures, we're going to do pH3. Remember, you put P in the middle because there's less of them. Then you count up your valence electrons. Let's see, phosphorus is going to have 1, 2, 3, 4, 5 valence electrons. And we're going to add those 5 to how many hydrogen it has, and hydrogen just has the 1 since it's the first block. So that's 5, 6, 7, 8. That's a total of 8 valence electrons. Let me get my pen back here. 8 valence electrons. We start on the outside, but you remember that hydrogen does not get dots there. So we're going to take those back off. Oops, I can't take them back off. Let's see if I can erase them. There we go. No dots on the outside, and then we go to the inside. We've already used 6 in the bonds. In these bonds, we've used 2, 4, 6. So then that means the last 2 are going to go on the central one. So I think that's going to turn out to be the answer, is pH3 has 1 unshared electron pair. But the other ones, by the way, that one's pretty easy to draw. If you were drawing this one, you might wonder, well, how do we do that? Well, when you're doing something that just has hydrogens and carbons and even chlorines, remember, generally speaking, the carbon goes in the middle because it's the least electronegative. Since we're just reviewing ideas, chlorine's here, hydrogen never goes in the middle because it can't have more than 2 electrons, so carbon almost always goes in the middle. So you would draw it in the middle, and then you just have the 2 H's. You could put them anywhere you want to. I'm going to spread them out on the opposite sides, and then you'd have the 2 chlorines. So that would be your basic structure, and then you could add up the valence electrons. Each chlorine would contribute 7, that's 14 total. The carbon would contribute 4, 1, 2, 3, 4. So that gets us to 18, and then the 2 hydrogens, 19 and 20. And so then you would just start spreading them around the outside, not doing the hydrogens because they don't get any, just sort of like that. And then you should be done. 16 is really asking us about intermolecular forces, because they want to know which of the following lists of species, remember that means things, is in an order of increasing boiling points. So the highest boiling point one is going to be last, so it's going to be the one that has the strongest intermolecular forces. So if we're going to list these 3 things, remember we have hydrogen, nitrogen, and NH3. I think we could all identify that NH3 definitely is going to have the highest boiling point, and the reason is because its intermolecular forces between it and another NH3 molecule would be H bonding, and hydrogen bonding is a particularly strong intermolecular force. Nitrogen and hydrogen, both of those are nonpolar molecules, so the only type of intermolecular force they have are London dispersion forces. And if you were guessing which one of those would have stronger London dispersion forces, you would guess nitrogen, because nitrogen has more electrons. They're in a fluffier cloud, has 14, 7 for each one. Hydrogen only has 2, and so this has stronger London dispersion forces. So this is sort of going to be the one that goes in the middle, and hydrogen is definitely going to have the lowest boiling point, which makes sense because we think of hydrogen as being a gas, although nitrogen is too. So we got to put them in that order. It says increasing boiling point, so it should be hydrogen first, nitrogen, then NH3. So it looks like A is going to be the correct answer. And then 17, which of the following molecules listed below has the largest dipole moment? Remember, that means they're saying which of them is the most polar. That's what largest dipole moment means. So we can rule out right away chlorine. We don't even need to really draw it, because no matter what happens, chlorine is going to be connected to chlorine. It could be a double bond. It's not. It could be a triple bond. It wouldn't matter. They pull with the same electronegativity on each other, so definitely going to be non-polar. HCl is going to be polar, I believe. If we actually drew its proper Lewis structure out, you'd find that that's what it looks like. And I'm shortcutting it. You definitely want to count the valence electrons and spread them around the outside. Remember, none of them go on hydrogen. It only gets the 2 in the bond. So that's definitely a polar one because there is a net dipole moment. If we were going to draw out the last 2, I'll do that. So SO3 would look like this. We would have, I believe, 24 valence electrons to work with. We'd spread them around the outside first. Then we would see how many we have left. So we've done 8 times 3 is 24. We've used them all. There's none left on sulfur. And so at this point we need to take some electrons off. So I'm going to take these 2 right there and drop them down and share, because sulfur only had originally 6 electrons and now it has 2, 4, 6, 8. So that looks pretty good. Now you notice that means there are 3 directions coming off of this sulfur atom, so it's going to be trigonal planar, so it looks pretty much how I've drawn it, and there is going to be no net dipole moment, as in they all are going to pull in offsetting directions. The double bond really doesn't have anything to do with that. It just has to do with the electronegativity of the oxygen. So we can rule a C out. It has no net dipole moment. And then let's look at NO. N is connected to O. N has 1, 2, 3, 4, 5 valence electrons. O has 1, 2, 3, 4, 5, 6 valence electrons. So we're going to add up to 11. 11 valence electrons, which is kind of odd because it's an odd number. If we were going to try to spread them out, we'd choose to go on the outside, and there is no outside, so I'm going to go like this: 1, 2, 3, 4, 5, 6, 9, 10, and we have one more kind of like that. So you notice that nitrogen's not happy, and you'd have to end up sharing, and it's going to be difficult to make this one happy anyway. But in the end, it doesn't really matter how it's connected. The O is going to be more electronegative, and it's going to pull in that direction. So these 2 are possibilities because they're both polar. Now I think B is going to be the correct answer, and the reason is because there's a bigger difference in electronegativity between chlorine and hydrogen than there is between nitrogen and oxygen. I mean, they're both right next to each other. Fluorine's the most electronegative. Both of these are pretty electronegative. So there's not going to be a very big oxygen will pull a little bit stronger than nitrogen, but not by much. So they're going to be sharing fairly evenly. So I think B should be the answer here.